In part 1 of our video on the basic theory of ANOVA, you learned that when we conduct an analysis of variance, we calculate two values that are both unbiased estimates of the population variance when the null hypothesis of no differences among the means is true. Those estimates are called the between groups mean square and the within groups mean square. You also learned that the between groups mean square is a measure of both treatment effects, if any are present, and experimental error. The within groups mean square is a measure of only experimental error. We are now going to expand on those concepts to show you how they can be used to make a decision whether or not any differences observed in the sample means should be attributed to the effect of our experimental treatment, or only attributed to random sampling error. If we decide that the differences in the sample means were most likely attributable to sampling error, we would fail to reject the null hypothesis that the means in the population were actually different from each other. On the other hand, if we decide that the differences in the sample means were more likely attributable to our experimental treatment, we would reject the null hypothesis in favor of the alternative hypothesis that at least one of the means was different than the others in the population. However, in order to know whether either of those conclusions are warranted, it is important to know whether the assumptions that underlie our ability to make them have been met. These are the assumptions about the nature of the data that was analyzed and are generally referred to as the assumptions for a one-way between subjects analysis of variance. There are three of them. They are normality, homogeneity of variance, and independence of error. The assumption of normality states that the data we are analyzing are random samples drawn from a population that is normally distributed. The homogeneity of variance assumption states that variances of the populations from which the samples were drawn are all the same. The independence of error assumption states that the error in one person's score is independent of the error in any other person's score. Because error is responsible for the variation of the individual's scores, another way of saying the same thing is that knowledge of one person's score will not provide any information that will enable us to predict any other person's score. The errors, and therefore the scores, are not correlated with each other. There are statistical methods available to check the viability of these assumptions that we will not cover in this video. However, we can say that with one exception, analysis of variance is generally robust to violations to these assumptions, especially when the sample sizes of the groups being analyzed are equal. The exception is the independence of error assumption. If this assumption is violated, the likelihood of drawing an incorrect conclusion from the analysis will increase. ANOVA is not robust to the violation of this assumption. We will now discuss how we draw conclusions about whether or not to reject the null hypothesis in an ANOVA. We have said that when the null hypothesis is true, the between groups mean square and the within groups mean square are independent, unbiased estimates of the same population parameter, the variance. In the population, then, the values of those mean squares would be exactly equal to each other. So under those circumstances, if we calculated the ratio of the mean square between groups to the mean square within groups, the ratio would be equal to 1. When the null hypothesis is false, however, and the group means vary from one another, the size of the between groups mean square will increase due to the presence of the additional variance due to the variance of the means. In this case, the between groups mean square will be larger than the within groups mean square, causing their ratio to be greater than 1. However, as usual, we are dealing with random samples drawn from the population, so the values we obtain for the mean squares will be subject to sampling error and will vary from the true unknown population values. Therefore, just because the ratio of between groups mean square to within groups mean square is greater than 1, does not automatically mean that the means of the groups are different in the population. That will depend on how much larger the ratio is from 1, and what the probability is that if the between groups mean square and the within groups mean square are really equal to each other in the population, we could have drawn random samples that varied from each other by as much as our samples do. In this section, we will start by asking the following question. If the result of our ANOVA shows that the between groups mean square is bigger than the within groups mean square, how large must this difference be for us to infer that the means of the groups are different in the population? In other words, how big does the ratio of the between groups mean square to the within groups mean square have to be for us to reject the null hypothesis? This question is answered using the F distribution. The F distribution is the distribution you would get if you repeatedly took two random samples from a normally distributed population, calculated the variance of each one of the samples, and then plotted the ratio of their variances on a graph. In other words, the F distribution is a sampling distribution of the ratio of two variances. This is the same concept that we discussed in our video on the central limit theorem when we spoke about creating a sampling distribution of sample means. The difference in this case is that we are interested in the ratio of two sample variances instead of the sample means. Because we are interested in determining if the ratio of the between groups mean square to the within groups mean square is statistically significantly different from 1, we can use the characteristics of the F distribution to make that determination. The ratio that we form using the between groups mean square and the within groups mean square is referred to as a F ratio. The F ratio is the test statistic that we use in ANOVA to determine whether or not to reject the null hypothesis. Because the F ratio is the ratio of the between groups mean square to the within groups mean square, both of which are variances, we can use the characteristics of the F distribution to estimate the likelihood that the F ratio we observed in an ANOVA could have occurred simply by chance. We will show you exactly how this is done later in this video. But first, we have to tell you a little bit more about the form of the F distribution. The form of all F distributions depends on the number of degrees of freedom associated with the variances that were used to create it. As we said, the F distribution is a sampling distribution formed from the ratio of two variances. Each of the two variances could have been calculated using samples of different sizes. Therefore, the degrees of freedom associated with each variance could also be different. The form of an F distribution will change, depending on the number of degrees of freedom associated with the variances used to create it. As a result, the F distribution is actually a family of different distributions that will vary depending on the degrees of freedom associated with each of the variances. Because we are creating a distribution from the ratios of two variances, there will be degrees of freedom associated with the variance used in the numerator of the ratio, and degrees of freedom associated with the variance used in the denominator. In an ANOVA, the degrees of freedom for the F test will be based on the degrees of freedom associated with the between groups mean square, which is used for the numerator of the F ratio, and the within groups mean square, which is used for the denominator. As you learned in part 1 of our video on basic ANOVA theory, the degrees of freedom in a one-way ANOVA for between groups mean square is the number of groups minus 1. The degrees of freedom for the within groups mean square is the number of observations in the study minus the number of groups. Let's take a moment now to reinforce these ideas by simulating how an F distribution is actually created. On the screen, you will see a portion of a set of 512 random samples drawn from a normally distributed population of size 2000. Half of the samples drawn were size 11 and half were size 26. We have calculated the variance of each sample, which is shown at the bottom of the columns. For this demonstration, we are treating the samples in pairs. The first pair consists of samples 1 and 2, the second pair consists of samples 3 and 4, and so on. We have calculated the ratio of each pair of variances. These also appear at the bottom of the columns. As a result, we have created 256 variance ratios calculated from random samples drawn from a normally distributed population. If we plot these ratios on a graph, the resulting distribution is a small-scale sampling distribution of the ratio of sample variances. This is what an F distribution actually is. If we were able to perform the same operation with an infinite number of samples, the resulting distribution would be an F distribution. As you can see, the general shape of our histogram created from the 256 variance ratios looks very similar to what the true F distribution based on the same sample sizes looks like. Of course, we only graphed 256 variance ratios, so the resulting graph is only an approximation of an F distribution. If we had been able to take more samples, the distribution would have been a closer approximation of the true F distribution based on an infinite number of samples. But the point of the demonstration was to show you how the F distribution can be approximated by plotting the ratio of variances randomly sampled from a normal population. Our example F distribution was based on variances calculated on sample sizes of 11 and 26. Therefore, the degrees of freedom in this example were 10 and 25. When the F ratio is calculated in an ANOVA, The degrees of freedom used for the F ratio are the degrees of freedom associated with the between groups mean square and the within groups mean square, respectively. In hypothesis testing using ANOVA, we often use a decision rule that sets the alpha level at 0.05. You are probably already familiar with this idea from your study of other inferential statistical procedures. This decision rule states that if the observed ratio of the two mean squares is small enough that it would occur more than 95% of the time when the population mean squares are actually equal to each other, we would attribute the observed variation in our sample means to sampling error. As a result, we would not reject the null hypothesis that the means of our groups were all the same. On the other hand, if the observed ratio of the mean squares is large enough that it would occur 5% of the time or less when the mean squares were actually equal to each other in the population, then we would reject the null hypothesis that the means of our groups were the same, in favor of the alternative hypothesis that at least one of the means was different from the others. We will now show you how we use the F distribution to determine whether the ratio of the between groups mean square to the within groups mean square is large enough for us to reject the null hypothesis that the means of our groups are equal in the population. For this discussion, we'll assume that we are analyzing the results of an experiment that contained 4 groups of 25 observations in each. The degrees of freedom for the between groups mean square would be the number of groups minus 1, which equals 3. The degrees of freedom for the within groups mean square would be the number of observations minus the number of groups. In this example, it is 100 minus 4, which equals 96. So we would use an F distribution that has 3 and 96 degrees of freedom for our analysis. To begin, we first must determine how big the F ratio needs to be for us to reject the null hypothesis. This value is known as the F critical value. To determine it, we first have to define how sure we want to be that if we reject the null hypothesis, the decision will be correct. This is what the alpha level that we talked about earlier represents. It must be decided upon before the experiment is conducted. While it can be set to anything that the experimenter feels is appropriate, it is most common to set it at 5%. When the alpha level is set to 5%, or equivalently at 0.05, it means that if we reject the null hypothesis, we are willing to accept the long-run risk of being wrong 5% of the time. We refer to this as the probability that we will make an alpha error. An alpha error is the error we would make if we rejected the null hypothesis when it was in fact true. As you may have already learned, it is also called a type 1 error. Of course, when we actually conduct a study, we can never be 100% certain that the inferences we draw about the unknown population values are true. The best we can do is to estimate the probability that they are. Once we have made our choice of the alpha level, we would use either a table of critical F values, or more conveniently, a computer application to determine what the critical F value is for the degrees of freedom in our study at the alpha level we have chosen. In our example of an experiment with 3 and 96 degrees of freedom and an alpha level of 0.05, the F critical value is 2.7. This indicates that when the null hypothesis is true, F ratios equal to or larger than 2.7 will only occur by chance 5% of the time or less. So if we have calculated an F ratio that is equal to or larger than 2.7, that value is too unlikely to have occurred simply by chance for us to conclude that the null hypothesis is true. Therefore, we would reject it. If we ran the same experiment 100 times, this conclusion would be correct about 95 times and incorrect 5 times. Therefore, about 5% of the time, we would have made an alpha error by rejecting the null hypothesis when it was in fact true. We will now show you this graphically using an F distribution with 3 and 96 degrees of freedom. Here is the F distribution that we would use to interpret the results of the study used in our example. Remember, the F distribution is a family of distributions that will look different depending on the degrees of freedom used to construct it. The area shaded in blue comprises 95% of the total area of this F distribution, and the red shaded area comprises 5%. Assuming we set the alpha level to 0.05, the F critical value will be 2.7. The numbers along the bottom axis are F ratios. In an analysis of variance, these ratios would be interpreted as the ratios of the between groups mean square to the within groups mean square. F ratios that fall outside of the blue area are unlikely to be observed if the mean squares are actually equal to each other in the population. An F ratio equal to or larger than 2.7 with degrees of freedom of 3 and 96 will only occur 5 times out of 100 or less, when the ratio of between groups mean square to within groups mean square in the population is equal to 1. That is, while it is not impossible for the F ratio of 2.7 to 1 or greater to occur when the mean squares are actually the same in the population, it would be very unlikely. The between groups mean square and within groups mean square would most likely only be this different if at least one of the population means from which our samples were taken was not equal to the others. So in this example, if the F ratio that we obtained in our ANOVA was 2.7 or larger, we would conclude that it is statistically unlikely that all the means are equal to each other in the population. Therefore, we would reject the null hypothesis in favor of the alternative hypothesis, which states that at least one of the means is not equal to the other means. In statistical terms, we would say that if the null hypothesis were true, the probability of obtaining an outcome such as this, called the p-value, is equal to or less than 0.05. In conclusion, it is important for you to know that if we reject the null hypothesis that the means in the population are equal, in favor of the alternative hypothesis that at least one of them is different than the others, this is only the beginning of the analysis. We would only know that the means are not all equal to each other, but we don't know statistically which ones are most responsible for the differences. To determine that, we have to conduct follow-up analysis, which are called post hoc tests. We will not be discussing those tests in this video, but they are important for you to learn about in your subsequent study of analysis of variance. This concludes part 2 of our video on basic ANOVA theory. In our next video, we will demonstrate all of the concepts we covered in these videos, using in-depth computer simulations of analysis of variance. These simulations are designed to reinforce the material that we have presented in these lessons. We hope you found our presentation valuable. Thank you for watching.